Yes.
So as we're looking at this extremely exciting and interesting problem,
Yes.
talking about people working for General Electric, they produced the LED light emitting diode. Today LEDs are in lots of cases. This book is still a bit outdated too. I mean, LEDs lighting is used in tons and tons of places. My dad is an electrician. He's obsessed with them. They're really efficient, good lights. Anyways, these two people, Chiara and Wawait, were asked to determine how many of these lights lasted less than 10,000 hours. Now, they were given this information, that they tested this many, that they figured the mean is 12,000. Yes, you guys are very funny. But you should still listen when I'm teaching. In spite of your hilarious looks, I still want you to be able to hear. And the standard deviation is this. They were asked to solve how many are less than 10,000. So initially, this person did z-score of 10,000. So they took the score of 10,000, subtracted the mean, divided by the standard deviation. They found a z-score of negative 0.57. They looked on their z-score table, which I'll remind you, you have one right here. I'm looking for negative 0.57. So I go to here, negative 0.57, and I find that's 0.2843. Yep. That's great. 0.2843. And so then, what should we say? So what should we say here? It's saying this is the probability. Yeah, Nathan?
Sir, yes, sir.
And this many light bulbs were tested, so how can we find how many light bulbs? Probably take the amount and multiply by the probability. And we get, what's that? $710.75. How many would we say here? Would we say 710 or 711? You're like I love going to 7-Eleven.
It's the exact number.
If I say 7-Eleven, I get a free Slurpee.
7-Eleven.
If we're talking about the exact number of light bulbs,
They pay me a point.
Yeah, exactly. The question is really, in a case like this, would you round up or round down to how many? I guess there's no real rule of thumb. Now, in this case, this student knows that a problem for z-score doesn't need to be calculated when using the distribution. So they just did a normal CDF. So let's remember how we did this yesterday. Second distribution. Normal CDF, not normal PDF. I noticed this is a different. One is a different calculation. Don't just mindlessly hit one. And then lower, a really low number. Yeah, that's a really low number. Sounds good. Upper, 10,000. How many under 10,000? With mean of 12,000 and a standard deviation of 3,500. Paste that. Oh, cool. Wait, but it wasn't exactly the same. It's really close, but not exactly the same. I got, in this case, 0.2838. And then take that and multiply it by 2,500. And I'll actually use the whole thing that my calculator used. So I'll say answer times 2,500. And I see, oh, this wasn't exactly the same. In this case, it was 709.6 or 710. Not exactly the same. Well, why is that? Why weren't they the same?
Maybe it's just the low number you chose. Exactly.
Oh, that's a good thought. That actually isn't it in this case. That's a reasonable. Jaden's thinking, wait, is it that I didn't go low enough on the bottom end? It's possible that's not the case here. It's actually, I'll tell you, the error is on this one, not on this one. This will be more precise. And the reason why is your calculator is accounting for way more than 4 digits. whereas your stats table is just giving you 4 digits, which is usually plenty. But when you're taking that number then and multiplying it by 2,500, you're introducing more information than that. So that's why there's a small amount, is that this is just using a number to 4 digits, whereas this is using a number that's actually much further.
Just a rounding error.
It's just a rounding error, but it's like when you're rounding something too close and then using that number. It's yes, it's a rounding error, exactly.
So you round it down,
No, this is just bad luck that it happens to round up. It could have been going the other way, but these are both fine, right? When we're talking about a sample of 2,500, is one light bulb actually meaningful in that sample? No, it's not.
so you wouldn't mark it wrong?
No, these are two ways of finding the amount that are missing in a sample like this. But you can think about this. In a sample of 2,500, is the difference between one light bulb working or not, is there likely to be some error in that? Yeah, there's likely to be an error in the data of one anyway. So
if it was a question on a test and there was like a rounding error,
if it was someone else, I'd give them grace. If it was you, I'd give it to you wrong.
Okay.
Yeah.
Okay, specifically, Troy.
No, I'm just saying, I recognize that in a case like this, the tool you're using determines how precise it is. Now, Aurora is considering producing 70,000 of these. Okay, 70,000. So using this method, how many LEDs could we expect to last between 10,000 to 13,000? Okay, well, I've been told to use this normal CDF method, so I'm going to do that. So second distribution, normal CDF. And in this case, lower, 10,000. Upper, 13,000. Mean is the same. Standard deviation is the same. So let's paste that. Let's see what we get. So what's the likelihood? Well, the likelihood is 0.32859 blah, blah, blah. And they're thinking of producing 70,000 LEDs. So we're going to multiply this probability by how many LEDs. And we predict that 23,002 LEDs. That's what we predict there. It's kind of a nice tool here. And then let's use this again. Of the 70,000, how many will be the really good ones? How many will last more than 15,000? So let's go vars CDF. Now this case, our lower is 15,000. Our upper is some really huge number. Good. Same stuff. Boom, boom. So the likelihood that it's up there is 0.19568, blah, blah, blah. Remember, we're multiplying by how many bulbs in the sample. And we suspect that 13,698 of those bulbs will last longer than 15,000 hours. So far, is it making sense? So we're using the normal CDF function to tell us what percentage of the bell curve that fits within, and then multiplying that by the sample. Now, I know for lots of you, the picture of the bell curve is helpful just in terms of thinking what we're doing. So in this case, what we were doing is we were saying, okay, we had this curve which had a mean of 12,000, which every one standard deviation was, whatever, 3,500. So really, this one we were asking, okay, which of the things were between like here and here? Next, we were asking which of these things are like above here, right? We're just asking which part it fits within the table in whatever spot. Okay, wow, that's a lot of me blabbering. How about another one? So instead of just doing it within the bell curve, we could do it within distribution. That's what we were doing. And as we said yesterday, left, negative, big number. To the right, positive, big number. Let's try this. Let's try this one. I think probably what would be realistic, let's do class example 1 and class example 3, and then I'll let you work. Sound good? Yep. I recognize the looks on your eyes tell me that we are worthwhile to do some more practice, but yeah?
We already did one.
Ah, that was one of the ones yesterday.
Just do 3.
Outstanding. No, 2 is good though. Yeah, we'll do 2. Thanks. So, appliance distribution company knows an average life of toasty toasters is 4.2 years. Oh, stop. Stop. What do I do? I got a number. Where do I put it?
That's the mean.
That's the mean. Okay, that's this.
Oh.
Nice. Let's label our diagram. Oh, standard deviation.
0.65. That's standard.
Nice. And the data is normally distributed. Okay, nice. Company does not want to replace under warranty more than 8% of the toasters that are sold. Okay, so it's saying it wants to set the warranty at a spot that this is 8%. Right, that's what it wants. It wants us to get a Z-score that makes it so the area is not more than 8%. Okay, wait, not more than 8%. So would 8 be okay? 8 would be okay, but not more than 8. So a maximum of 8. So in number of years, what warranty should the company offer? Okay, let's think about this. So how could I set something like this up? We're trying to find what would give us an 8% area over there. How do I do that again? Remember yesterday we had one way of finding kind of what the area is, and one way of doing what's the Z-score if we know the area? Oh, nice. Yeah, the only other option we did yesterday. Okay, inverse norm. So let's try that one now. Let's try that one. Okay, so distribution. So with an inverse norm. Okay, wait. I don't remember what I do now. I'm lost. So first of all, what's the area that I need here? Not more than 8%. So let's just say, okay, area 0.08. Okay, what's the mu here?
4.2.
Nice. Standard deviation?
0.65.
Wow.
And then to the left.
And, oh, good. And tail is to the left. Awesome. And remember, if you have a TI-83 or an earlier 84, you only have the option of tail to the left. Okay, let's see. Paste. Boom. Whoa. What's it telling us? Okay, so the inverse norm of this 4.2, 0.65, and L gave me 3.287 blah blah blah. So what would be a reasonable warranty to give? Probably you're not going to give a partial year. So would you pick a 20-year warranty? That's a great idea. Really smart.
3.3.
No, but we probably don't want to do a partial year. So should we pick a 3-year warranty or 4-year warranty? Which one would not let us go more than 8%?
3.
Right, 3. Okay. By the way, this is another one where I think knowing that we're probably just talking about full years in a case like this, guess and check is probably a perfectly valid option, eh? If you're like, I don't remember inverse norm, but I can do this normal CDF, you could just try 3 and try 2 and try 4. Not so hard. But this is a good tool. Nice. All right. One more. Oh, 62.3% of the shrimp harvested at this had a mass of more than 135. Now, just thinking about this, is 135 then to the left or to the right of the mean?
Right. Because it's more than.
Well, yeah, but 62% is more than. So if the middle is 50%, I think this is going to be somewhere over here, hey? 135? Because 62.5% needs to be that way from it. And the mean, okay, yeah, we see that. The mean is 146. Determine the standard deviation to the nearest tenth. So now I'm asked to find sigma, huh? That's kind of hard, hey?
Can't use that sigma formula.
Oh! Maybe. I didn't know how to do this. I need help. So, yeah, we need to find the standard deviation. I have my Z-score.
Yeah, you have that score.
What's my Z-score for this point?
62.3.
Just be careful. That's what's to the right of it. So what's my Z-score? Isn't Z-score what's to the left of it? So wouldn't my Z-score be 1 minus 0.623? Yeah? So I know, okay, my Z-score formula Z equals X minus mu over sigma. And I think from this, actually, I have everything I need. I think I don't need to put a fancy calculator formula. I think that I have enough here to just use Z-score formula to find this. So my Z-score, now that I've taken the whole, subtracted out what's to the right, I have what my Z-score was. My Z-score is 0.377. Wait, that's not true, is it? That's not my Z-score. Sorry, I'm lying. I have my area under the curve. I don't have my Z-score. Can I find my Z-score from my area under the curve, though? Can I find that? Use your table or use your inverse norm. Either way, I mean, use your normal CDF. Either way is fine. I'm going to, just because I have my calculator here and the table's in the back of the book, I'm going to go second here, normal CDF. I want to know the area from low up to... Wait, that's not true. Backwards. Inverse norm. Area of 0.377. So this Z-score is equal to negative 0.31336, blah, blah, blah. Okay, so if I have all this stuff now, negative 0.313, probably enough, equals X 135 minus mu 146, all divided by sigma, which I don't know. So to find this, sigma equals negative 11 over negative 0.313. Sound good? Now, I found it a little confusing, that one. There probably was a simpler way to do that now that I think about it, but I felt a little bit confused there, so I just want to check this. I want to see if this seems reasonable. When you have a Z-score of -1, what's the area? Can you check your table? When you have a Z-score of -1, what's the area to the left?
0?
No, just look at your table. Z-score of -1. Okay, 0.1587. Now let's take a look here. So we're saying that the standard deviation is 35.1. So the standard deviation is one standard deviation to the left would actually be like, whatever, 110, something like that. And in that case, 0.157, is that what you said, Lacey? 15%? Something like that?
Yeah.
So 15% to the left of that, whereas this one we see 37% was to the left of that. Does it make sense that this is about midway in between Z-score of 1 and Z-score of 0? Okay, yeah. So it's like, okay, I felt a little confused as I was doing that, but I now check. Like, this is somewhere between Z-score of 0 and Z-score of -1, somewhere in the middle. And I'm about midway in between my standard deviation. Yeah, that makes sense. Seems good. Cool? Okay.
Is that a 9 or a 4?
Where?
35.1. Is that a 4?
What are our units?
Oh,
Good.
oh, that's me.
All right, I would like you to do question 1. 1, 2, 3, 4, 5, 7, 8, and 12 and 13. Yeah. There we go. Nice work, team. I'll get these little quizzes marked and back to you.